Hello everyone, welcome back. This is lesson 5 of our machine learning fundamentals course, whereby today we're going to be covering model evaluation, metrics, cross-validation and tuning. So some key points of what we'll cover in today's session. We'll look at why evaluation is crucial for obtaining reliable results. We'll look at some of the core metrics for classification, regression and clustering, and we'll take a look at some practical methods as well. So firstly, why does model evaluation matter? Why do we evaluate our models after we have created them? Well, first of all, decision making. So if you think about in a real world scenario where you have a business or researchers that are relying heavily on machine learning outputs to make strategic decisions, then of course inaccurate models is going to lead to poor outcomes. Secondly, we have things such as bias detection. So sometimes your data might have biases, or the model might be overfitting. Remember when in previous lesson we looked at overfitting and underfitting, whereby overfitting is when the data is too accustomed to the test data set. In other words, it's test specific. So on test data it performs really well, but it's memorizing too much the key words and phrases, and it's just too accustomed to the test data. So when it's presented to new data, it doesn't know how to respond and it's not performing so well. So evaluation metrics can help to catch and mitigate these issues. Thirdly, comparison and tuning. So when trying multiple algorithms, we need consistent metrics in order to compare performance and choose the best model. And finally, for continuous improvement. So models often need to be retrained or improved. Proper evaluation methods help to form the foundation for ongoing enhancements. Evaluation metrics for supervised learning. So we have different metrics for measuring a model's performance, whether we're using supervised or unsupervised learning. So firstly, for supervised learning, classification metrics. So we use what's known as accuracy. The definition of accuracy is how many times the model got it right out of all its guesses. So one pitfall can be misleading. It can be misleading if the data is imbalanced. For example, 95% not spam, 5% spam. You could guess not spam every time and still get 95% accuracy because the initial testing data is imbalanced. Or the initial data, I should say, is imbalanced. Next, we have terminologies known as precision and recall. So in other words, we would call these the true positives, dealing with the true positives versus true negatives. So what is the definition of precision? Precision is of all the items that you predicted, that the model predicted as positive or spam, how many actually are spam, are positive. So example, in a spam detection, of all the emails labeled spam, how many really are spam? And this is not to be confused with recall, which is similar, but it is different in what it's trying to assess or analyze. So recall says that of all the actual positives in the dataset, how many did you catch? So if we look at our spam example, it's of the total pool of spam emails, how many did you even catch and then correctly label as spam? So precision just says, okay, let's say we have 100 emails, and out of those 100 emails, there was 60 that were spam, but you managed to catch 50. But let's say of those 50 that you managed to catch and you labeled as spam, 100% of those actually were spam. So the precision score would be 100%, but the recall score would not be 100% because there was still 10 that was missed, because we had 60 that were meant to be marked as spam, you only caught 50. But of the 50 that you did label as spam, they were correct. So that's the difference between precision and recall. And then we have something known as the F1 score, which is essentially a combination of the precision and representation of precision and recall by combining the two to get a general overall score of a general overall accuracy score of how well the model performs. So the formula is true positives plus true negatives divided by all the predictions. So again, it's great when you need a single number to balance precision and recall, especially for imbalanced classes. So classification and regression metrics. We have what is known as a confusion matrix. What is a confusion matrix? It is a table showing actual versus predicted classes. So it helps you see where errors occur. For example, are you misclassifying positives as negatives, for example? Regression metrics. So we have mean squared error, which we have discussed previously, which is the average of squared differences between predicted and actual values. It penalizes large errors more heavily, brackets, by squaring them. We also have mean absolute error. This is the average of absolute differences. It's more robust to outliers, meaning anomalies, than MSE, but it doesn't penalize them as strongly. Lastly, we have R squared. So this measures how much variance in the data is explained by the model. So closer to 1 indicates a better fit. 0 means it's no better than simply guessing the mean, and a negative value means it's even somehow worse. So evaluation for unsupervised learning. So we've looked at now evaluation for supervised learning and the accuracy, precision and recall. But what about unsupervised learning? Because with unsupervised learning, we don't have labels to actually check against to see, okay, whether this is spam or not spam. We knew from the get-go which emails were spam due to the labels. But for unsupervised learning, how do we check whether what we're doing is correct? So, of course, no labels. In clustering tasks, you often don't have the correct answers. So we have these different methods known as, for example, silhouette score, which we're going to take a look at, as well as Kalinski, I don't really know how to say this, Kalinski, Harabas, and the Davies-Boolean index methods. So silhouette score measures how similar an object is to its own cluster compared to other clusters, and it ranges from -1 to 1, higher is better, meaning well-separated clusters. We have the Kalinski, Harabas, and Davies-Boolean index. So these are other clustering metrics that balance intra-cluster cohesion with inter-cluster separation. And remember this pro tip, sometimes you can label a sample of data post hoc to check clustering performance, but domain knowledge is crucial, for remember that we are working with unsupervised models and we don't have labels to act as that trainer and that guide and that teacher for the model. Alright. So what is silhouette score? It's visualizing the clustering quality. So I have an analogy for you. So imagine a party analogy. So like friend groups at a party, good clusters will show a clear separation between groups. Well clustered data groups, similar points together and different clusters apart. How is it calculated? So it's calculated by A equals the average distance to points in the same cluster, known as cohesion. B is going to be equal to the average distance to nearest different clusters, known as separation. And so this is essentially the formula. You have B minus A divided by the maximum, all the data, times A and B. And it ranges from a score of -1 to 1. So interpreting the results of whatever the score comes out. So just bear in mind, what you need to know is that the higher scores near 1 indicate a well separated and cohesive cluster, and scores near 0 suggest overlapping clusters, which is not what we want. So negative scores mean points are likely assigned to the wrong clusters. So if we have a score closer to 1, it means our clusters are operating as they should, is what we want. So the Kalinski-Harabas index, this is the variance ratio criterion, a different method. So imagine the library analogy. So imagine it's like organizing books. This index measures how distinct each section is from the others while keeping similar items grouped together. And we have what's known as between cluster variance. This measures how spread out cluster centers are from each other. Greater distance indicates better separation between groups. And we have within cluster variance, measures how tightly packed points are within their clusters. Smaller spread indicates more cohesive grouping. And real world application, so for example in music streaming, Higher index values show clear separation between genre listeners with consistent patterns within each group. So this is all essentially what we've looked at in the last lesson, and these are methods to evaluate the groups that we have essentially made. A quick way to test our models and to see at a glance how well they are sorted and performing. Next, we have the Davies-Bouldin index. So imagine like a well-designed city. Good clustering creates neighborhoods where houses within each area look similar. There's clear boundaries between neighborhoods indicating effective separation between clusters. The calculation method, it measures the ratio of within clusters spread to between clusters separation. And so lower scores, closer to 0, indicate better clustering with distinct cohesive groups. So don't worry if you don't remember when you're working with all these models, if you don't remember exactly which one, the full interpretation of what each model does. But the most important thing to understand is the indication of what the score represents. So where you see a lower score or where you see a higher score, what does that represent in relation to how well your model is performing, right? That's the main thing that you need to grasp at this stage. Real-world application helps identify distinct user segments in social media data. High index values reveal problematic overlap between fitness enthusiasts and foodies group, for example. Next, we have the train or test split versus cross-validation. So the train and test split method, the basic method is to split your data set into two parts, be it 80% for training, 20% for testing, or it could be 70% for training, 30% for testing, or 75-25. It doesn't really matter too much. It's just custom to train on the larger portion and test on the smaller portion. The drawback to this method is that the performance estimate can vary depending on which data ends up in a test set. Next, we have cross-validation. So cross-validation, the concept is to partition your data into folds or segments, and you train on k-1 folds. Remember, k would be the groups or the clusters, and then we test on that remaining fold, and then we rotate. The benefit of this is it's more robust. It's a more robust estimate of model performance because every data point is used for both training and testing, i.e. via the different folds. So example, you have 5-fold cross-validation, means you train and test 5 times, each with a different test fold. And we're going to take a look at an example in a second. So a practical tip, use cross-validation when you have smaller data sets or need a reliable performance estimate. For very large data sets, a single train test split might be sufficient, but cross-validation is still more valuable if time, and resources permit. So, k-fold cross-validation. As we mentioned, it splits the data into k folds. So you divide your data set into k, a number of equal parts. Common values to use could be k equals 5, so 5 groups or 10 groups. The next step is to rotate the training and the testing. So for each iteration, we use k-1 of the folds for training and the remaining fold for testing. Okay, so if you have 10, if you decide to do k equals 10, so that means we'll have 9 folds for training, for k-1, so 10-1, 9 folds for training, and that remaining 1 fold we'll use for testing. And we repeat the k number of times. So since we had 10 groups, we're going to repeat this 10 times. And so each fold will serve as a test set exactly once. And then we essentially just average the results. So we calculate the mean performance, the mean average across all k iterations for a robust estimate. It's like rotating study group leaders. K-fold cross-validation ensures that every data point contributes to both training and testing. This reduces variance in performance estimates. And so we have a practical example here of k cross-validation. So cross-validation provides a more reliable performance estimate than a single train/test split. And let's see how this works with real data. So imagine now we're looking at houses, right? We're looking at housing. And so we're going to train on the sets 201 to 1000. So we split the training set into 5 different groups, and this is going to be the training set. So 201 to 1000 are the houses that we're going to be looking at as our training data, and then the houses between that are labeled 1 to 200, we are going to use that as a test set. And so let's say during that time, I don't know exactly what we're trying to calculate, maybe it's house prices or whatever it may be, we've got 85% accuracy score. Okay, and so now we're going to repeat it, except with the training set now, we're going to include what was previously a test set in the training set. Yeah, we're going to include what was previously a test set in the training set, and we're going to miss out what was previously the training set is now going to be the test set. Alright, so we're just simply going to miss out this training set. And so we're going to do 1 to 200, miss out the training set of the previous iteration, and do 401 to 1000. Okay, and let's say now we've got accuracy of 82%. Okay, and we just repeat the process. So the last one now becomes part of the test set, and we include the previous in the training. Alright, and we just essentially repeat that process. Calculate all the score and find out the mean. So our model achieved 85% average accuracy with plus 2.4% standard deviation across all folds. This narrow range indicates stable performance across different data subsets. Okay, a quick point to mention. So essentially what this score is saying is that we had 85% overall accuracy and a plus or minus 2.4% standard deviation. So in other words, it's saying that our results didn't deviate wildly. It didn't fluctuate wildly. If our results fluctuated wildly, let's say for example this training set we had 85, then we had 82, then we had 60, then we had 30, then we had 100%. There would be too much of a high deviation, which means that the model is not trustworthy. Its performance wasn't stable. Okay, and so there's different cross-validation methods beyond k-fold, and we're just going to take a very brief look at the definitions of what each one is, but I recommend it in your own time, depending on your level of interest, that you take a quick look at each of these methods in a little bit more detail. So first we have stratified k-fold. So this maintains class proportions in each fold. It's crucial for imbalanced datasets like fraud detection. Ensures fair representation of all classes. It's ideal for medical diagnosis with rare conditions. We have the leave one out cross-validation method. So this tests on one data point while training on all the others. It's perfect for small, precious datasets. It's computationally expensive, however, but it is very thorough. Next, we have the time series cross-validation method. This respects chronological ordering by training on past data to predict future events. So if you imagine, this is good for things like stock prices and weather forecasting, and it preserves temporal dependencies in data. Lastly, we have what is known as hold-out validation. So this is a simple train test split for quick prototyping and large data sets. It's the fastest validation method and is suitable for the initial exploration phase. Right, we also have something known as hyperparameter tuning. So what is hyperparameter tuning? It is a process of systematically testing different configuration settings, for example like learning rate, number of trees, or regularization strength, in order to find the combination that makes your model perform the best. So it's essentially similar to adjusting the temperature, time, and ingredients in a recipe in order to make the perfect cake. So we have different hyperparameter tuning methods. We have the grid search method. Systematically try all combinations of hyperparameters. It can be, of course, time consuming if you have many parameters. We have the randomized search. So randomly sample hyperparameter combinations within a range, often faster, and can find good solutions with fewer iterations. Or we can use automated tools such as the Bayesian optimization, for example, HyperOpt, OptTuner, or built-in scikit-learn methods. So these use more intelligent methods than brute force or random guessing, which is, of course, usually recommended. The hyperparameter tuning workflow. So first we split data. Divide into training and validation sets. We search for parameters, we try different hyperparameter combinations, evaluate the performance, measure model quality with cross-validation, and select the best model. Oh, it looks like some wording was cut off there. Here we go. So the workflow, combine cross-validation with hyperparameter tuning in order to get the best estimate of performance. So example, you could use the grid search cross-validation in scikit-learn, runs cross-validation for each hyperparameter combo and picks the best scoring model. So what does that look like? What does it look like when we put all that together? We split the data or cross-validate, 80-20 split or 5-fold cross-validation. We then train the model. We try a logistic regression or random forest, for example. We evaluate. We check the precision, the recall, the F1 score, and the confusion. Evaluate the confusion matrix. We tune the hyperparameters for random forest, number of trees, max depth, etc. Or use grid search CV or randomized search cross-validation. And then we do a final check, evaluate on the holdout or via cross-validation, holdout set or via cross-validation. We just are trying to ensure that there's no major drop in performance, so we're trying to avoid overfitting. And lastly, deployment. So once we're satisfied, we integrate into your spam filter pipeline and keep monitoring performance over time. In the spam example, in the scenario where you're building a spam classifier. Key takeaways. So we looked at different metrics for different tasks. So just remember, metrics differ for classification, i.e. precision, recall, F1, and also regression, MSE, MAE, and R squared, as well as clustering. We looked at the silhouette method, etc., etc. Reliable evaluation. Remember that cross-validation provides a more reliable performance estimate than a single train/test split. Remember the importance of tuning. Hyperparameter tuning can significantly boost a model's performance, but it must be done carefully. And honest assessment. So good evaluation keeps you from fooling yourself with misleading or incomplete metrics.